My name is Hakala. I'm a co-founder of Convion, and today in this third part of a series of 4 DEMOSOFC mini webinars, we'll be discussing about performance of the DEMOSOFC plant, the world's first industrial scale installation of SOFC fuel cells fueled directly by digested quality biogas. Along with me, discussing and presenting is Dr. Markus Rautanen from WWTP Finland. Hello, Markus. How are you doing?
Hello, Tuomas. I'm fine. It's nice and sunny outside.
Very good. Very good. Okay. We have structured and organized a webinar so that I will first discuss a little bit about the application and why performance and scale matter, how they are linked, and what is the expected and potential performance of this concept. And since WWTP has been involved and responsible of the performance analytics and measurement of environmental footprint or aspects, Dr. Rautanen will tell more about the actual results measured and determined from the demo plant. First, a little bit about the sort of rationale, why fuel cells and biogas, why they are a good fit, why this technology has potential to transform applications where so-called opportunity fuels are produced, local fuels that are non-standard, not like commodity fuels, but available locally as a product of a process or as a way of capturing value of an otherwise underutilized feedstock, and also how the essential services of communities, such as waste and water services, are affected by an ability to produce energy locally. Then, after I've talked about the concept and how performance is linked, Dr. Rautanen will show us the results. Wastewater treatment is a very energy intensive and essential service. In developed economies, it consumes about 1% of total electricity, or represent 1% of total electricity demand. It may sound small, but it's not insignificant, and on a municipal level, it can be a major or the major consumer of electricity. Something that is very important is that maybe we overlook here in European context, but very soon a large or even majority of the world's people will live in water-stressed areas, and those tend to be the same areas where water and waste services are not on a very good level. It is surprising that in the world, approximately 80% of all wastewater is discharged untreated, and that has major effects on livability of communities and health of the environment. Something that is very characteristic of wastewater, such as other household generated waste streams, is that it trickles down in small streams, and therefore majority of wastewater is treated in small and medium-sized wastewater treatment plants, and energy tends to be their biggest operating expenditure item. Here on the right-hand side, I have these two pie charts. If we take European wastewater treatment plants where the input feedstock is more than 20,000 population equivalent, the large majority of sites have less than 500 kilowatt technical potential of power generation. this is the chart on the left-hand side, 4,274 sites. And if we take all of these plants, starting from 20,000 population equivalent, majority of also the potential of biogas production is in these less than 500 kilowatt technical potential sites, which means that if 1% of total electricity demand comes from wastewater treatment, it actually comes predominantly from the small sites, since the very large ones are already optimized and often very close to energy autonomy. It's paradoxical because anaerobic digestion, the production of biogas as a sort of a byproduct of wastewater treatment, is a scalable and well-known process. And yet the penetration of combined heat and power generation is very small in this sector when we go down to medium and small scale. DEMOSOFC site is somewhere very sort of medium range in scale, a very typical one in European context, but also we can expect it to be in other continents. Solid oxide fuel cell, what is important and how performance is linked to this application and how this technology can transform the application is that not only it has the highest conversion efficiency from fuel gas to electricity, but that is also regardless of scale. And we can therefore make modular generators that are well matching with the available fuel. If locally produced biogas is sort of a free fuel, it's still finite, and therefore whether it makes sense to produce electricity locally depends on your total economics and how much particularly electricity can be generated out of the gas. Here in the chart you see electrical net efficiency as sort of like a ballpark estimate. Our systems are here between 53 and somewhat above 60%, and this is practically twice as much of electricity per year from a given amount of biogas. That's quite significant. When we go to wastewater itself, the curious detail is that it has more of embedded energy that is actually required for treatment of that wastewater. So there is a potential for energy autonomy, but as of today, it's realized only in those million population equivalent size units. But solid oxide fuel cell technology, because of its high efficiency, has a potential of changing that and making energy autonomy or near autonomy a realistic possibility also for medium scale facilities. We had a previous session about the site and engineering, and I will not go into the details, but the basic idea, concept, it didn't completely get realized in the project, but the concept was that we can cover 100% of thermal loads and offset 1,260 megawatt hour per year of grid electricity consumption by the facility. It would be all consumed on site because the electricity consumption is rather high, but it would be a very significant contribution to the total energy budget. Due to the advantages of this technology, produce practically zero local emissions, which means nitrous oxides, sulfuric oxides, particulates, hydrocarbons. And yeah, I can maybe then shift to Markus. You can unmute your microphone and tell a little bit about what actually then happened in the project and what kind of results we got.
So thank you. So let's talk about the performance of this first of its kind installation and also the emissions from this fuel cell installation. So if we first take a look at these two graphs here, so we have the efficiency, so electrical efficiency and total efficiency as a function of electrical net power output on the graph on the left-hand side. And on the right-hand side, you have the operating time as a percentage of the total operating time. So basically telling you how much time the system has been operating at each given region. So the lower graph is the electrical efficiency. So from that, we can notice that more than 50% of the operating time, so this is now accumulated operating time over several thousands of hours, including all the operating points. So more than half of the operating time, the electrical efficiency of the fuel cell system has been above 50%. And the total efficiency of the system has been above 85% for the majority of the operating time, which is, I think, quite nice numbers for this first installation. And what is also significant here, if you take a look at the shape of these graphs, so the dashed lines represent all of the operating points, and the dots or X's represent sort of the major operating points that have been that the system has been on in a very significant amount of time, or the majority of the time. And if you take a look at the shape of these curves, you can notice that the efficiency values, that high efficiencies, are not only reached at 100% load, but also at relatively low partial load. So let's say that from roughly 60% to 100% of nominal load, the both electrical efficiency and total efficiency stays at these high values, about 50% or about 85% in total. Yep. Next one, Tuomas. So one general advantage that people often quote for high temperature fuel cell technology is that they are able to operate at different gas compositions, different fuel gas mixtures. Here on this graph, we have actual measured data over a significant period of time of operation of this, this first of its kind installation. So we have the fuel cell system efficiencies on the vertical axis and the methane content of the fuel at the horizontal axis. And what you should notice from here is that the electrical efficiency and the total efficiency of the fuel cell system stays constant, independent of the biogas methane content. So even though the methane content is varying, it doesn't affect the system efficiency, which is of course very nice in this type of application where you can have significant fluctuations in fuel composition over a season or ambient temperature or any other aspect. Next one, please. So next few words about emissions. So why are we talking about emissions? Well, of course, everybody is talking about, usually first thing that comes to your mind is global warming and greenhouse gas emissions, which are of course super important, and what we are also trying to achieve here, reducing those. But it is not the only thing that matters. Another aspect of emissions is the local emissions that should also very much be reduced globally. These two pictures are from northern India. So the picture on the left is before this, of course, unfortunate COVID-19 lockdown, and the picture on the right is taken during the lockdown. So from this region, it has been about more than 30 years since the Himalayan mountain range has been visible, because there's so much local pollution from industry, from traffic, you name it. But now, due to the sort of declined amount of emissions in that area, the mountain range is actually again visible. I think this is a sort of pretty powerful message that or rationale why the local emissions are also really important to reduce, because they are really affecting the quality of life for billions of people on this planet. Next one. So what we have done in this project, we have actually went there on site to measure emissions from this first fuel cell installation. And let's look at the results. Can I get the next one? Yep. So first I want to show you what is the sort of emission level from a traditional or maybe I should say old-fashioned technology. So these bars here represent emissions from a biogas engine. So internal combustion engine, traditional engine, actually located in another wastewater treatment plant in Turin, Italy, having very similar biogas feedstock as the fuel cell system here. So if you start from the right of the graph, you notice that there's this big bar of methane there. Methane is very powerful greenhouse gas. It's about 30 times more powerful than CO2. So that is definitely something that they'd like to reduce in the future. And all of these other bars in here on the left, sulfur dioxide, carbon monoxide, nitrogen oxides, and particles, these are the local emissions that are affecting the environment locally. And these are something that definitely needs to be reduced also in the future. Why is it important for wastewater treatment? Well, the wastewater treatment usually takes place relatively near to where the waste is generated, meaning that this takes place in major cities. The bigger the city, the more wastewater treatment there is. Next one, please. So, like I mentioned, we went there on site, measured the emissions from the fuel cell systems. Actually, we could not detect any sulfur dioxide, carbon monoxide, nitrogen oxides, or methane from the fuel cell system exhaust. So we couldn't detect any of these compounds from the exhaust. All of the concentrations were below the detection limits of our instruments. Here in the graph, you can see some small blue bars corresponding to fuel cell system emissions. These are the detection limits of the instruments. So these are the absolute maximum that there can be coming out from the system. But like I mentioned, we couldn't detect any of these. The only thing that we could actually detect was particles in the fuel cell system exhaust, but the particle concentration in the exhaust gas, it was actually lower than the values in the ambient air. So basically, what the fuel cell system does, apparently there's some filtration in there, and the exhaust gas is actually, in terms of particles, it's cleaner than the air around the system. So what we have looked here is that this very first fuel cell installation, SOFC installation in a wastewater treatment plant, we have seen now very good, I think, very good performance, high efficiencies, not only at full load, but at partial load also, constantly high efficiencies at different fuel gas compositions, and very significant reduction in emissions as well. So back to you, Tuomas.
Okay, thank you very much, Marcus, for the slides and explanations. Just to say a few words about the results, I think as has been covered in the series of webinars and will also be talked about in the last seminar webinar next week. There's still a lot of work to be done. This technology is still under development and being commercialized, and many challenges are ahead of us. But what is quite interesting, I think, is that efficiency and negligible emissions are the ones that can easily already be achieved. The ones that are impossible or very difficult with conventional technologies. There's plenty of work to be done with standardizing the application interfaces and auxiliary systems and increasing robustness of control, and what we've heard, for example, in the previous presentation. But these very essential metrics of goodness of this technology, efficiency and emissions, local emissions, they can be shown to be very good, on a good level already. To conclude the discussion and enter the questions and answers part of this, wastewater is quite an exemplary application of integrated power generation technology. It is, by its very nature, distributed. So modular technology like SOFC is well suited for it. It is necessary, and whatever happens to the decarbonization of electricity overall, we humans remain part of the carbon cycle, and therefore the food and waste cycle contains carbon, and fuel flexible high temperature fuel cell technology can easily be adapted to various compositions of fuel without the necessity of costly gas separation technologies to reach sort of a commodity fuel level. To quantify a little bit the significance of this application, first of all, it's been estimated that 330 cubic kilometers of wastewater is generated per year in the world, and 80% of that is discharged in waterways untreated. And that is mostly water. It's just very small fraction of it is waste, and the rest of it is water. And by 2025, half of the world's population will be living in water-stressed areas. So I see that there's plenty of work at different scales to optimize and improve this function, and solid oxide fuel cell technology can play a significant part in small and medium scale particularly. In terms of greenhouse gas emissions, this is not a little fish either. 3% of man-made atmospheric greenhouse forcing is actually as a result of this wastewater sector. To wrap up, highly efficient modular solid oxide fuel cell technology with a power to heat ratio that matches well with the demands of wastewater treatment process, where anaerobic digestion is part of, has a potential of transforming the whole sector and make medium and small scale facilities also energy autonomous or approach energy autonomy. Due to the fact that most of the community sizes and agglomerations are so small that conventional technologies are just not feasible there. Okay, I think we can wrap up there. DEMOSOFC project still continues for some while, and we continue working on this application. The results have been encouraging, and lessons learned have been very important. I think we can enter the questions and answers session. There, I see that there are some questions already, and Marta, maybe you wish to control. You have the other channel for questions as well.
Yep. Thanks, Thomas, for the presentation. By now, I don't see any question on the other channel, so you can start maybe answering the 4 or 5 questions which are already in the chat.
Yeah, okay.
Yeah.
First question is, what happens with SOFC performance, meaning efficiency, when this methane content is below the 60%, say 40%? Well, first of all, solid oxide fuel cell systems can be designed to run on very diluted gases. Our systems, we have set a limit. It's not limit defined by the cells themselves, but the system and the thermal system particularly. We have set the limit for 55% molar of methane in order to reach a nominal output. If for temporarily the gas becomes more diluted, we can still carry on, but we have to downrate the system to some degree. What would then happen if we design the system for further down or operated at partial load? Electrical efficiency could be made to stay almost the same. Not big difference. Recoverable heat would probably be somewhat reduced. I don't now have simulations, but with the intended range from 55% up to 100% methane, we can reach practically the same level of efficiency for electrical efficiency. But if the gas becomes very diluted, the recoverable heat, of course, the same amount of heat is generated, but it's just harder to recover from streams that are much bigger. Any exhaust gas after treatment performed integrating with SOFC? No. Well, there's exhaust recycle. There is exhaust recycle, but not to mitigate any emissions or anything like that. But that's we recycle certain fraction of the anode of gas back to the system and mix it with fresh fuel, and this is to recover the steam that is in the anode of gas, and steam is needed for the steam reforming of methane, in this case, of other hydrocarbons if there were any. But we don't treat exhaust gas. There is an afterburner that combusts the tiny amount of residual combustible content in the exhaust. But other than that, there's none. Markus mentioned that there are less particulates in the exhaust than in the ambient air, and that is because we have filters in the air intake, not outlet. Okay, range of CH4 was given from 57 to 67. Does it mean that the biogas has a certain content after? I guess the persistent value for most persistent value for biogas methane content was somewhat above 60%, and the range Markus presented was from 57 to 67, a 10% percentage point spread, and this was due to variations in operating conditions in the digester. Of course, the raw gas that comes out of the digester is saturated with water vapor. It has impurities such as H2S and some minor impurities. Those need to be removed. There in the webinar number 2, Marta explained that the total implementation, including a chiller that removes water, and then the adsorbent beds that remove other impurities. I don't know, Marta, if you can comment, but I suppose the saturated water content, maybe 2% or 3% of water in the gas that comes out of the digester.
Yeah. Also because outside of the digester, I agree on your data. The biogas methane content, which was mentioned in the question, was just varying because of the digester operation, especially because of the quality of the biomass entering the digester, so the sludge. The cleaning, the purification system is not affecting the methane at all. Yeah, I agree with what Thomas said in general.
Yeah. What I mean is that when raw gas, if it has a couple of percentage points of water, when that is removed, then obviously the relative fraction of methane slightly goes up. But this is the ballpark, and the solvent itself doesn't change this.
Yeah, after the digester, there is in the SMAT, let's say, part of the plant, there is a gravel filter where most of the liquid or condensing water is removed. We have then some chillers. It could be, as you say, that the relative methane amount varies, but I think this is affecting of some percentages, not more. The rest are fluctuation in the methane.
Yeah, of course. We analyzed some like over a year profile of the digester and its output, and there are variations in amount and some variations also in the quality of the biogas. Even day by day, there are some maybe changing depending on the ambient temperature, or I don't know, profile of city vibe. I don't know what causes the differences, but there are some minor changes in quality, but the system can adapt. We had a sensor for measuring CH4. Because of the changes were quite minor and fairly slow because of the high volume of the gas holder, we would not see rapid changes in the composition, and that helped. We could probably control the system without the sensor, but it was of great help also for diagnostic and analysis purposes to have an actual online measurement. Then there's a question: does the methane concentration impact on the power density of the system? Was the cell operating voltage constant for the tests?
Well, Tuomas, I think you skipped one question there.
Sorry.
Yeah. There was a question about nitrous oxide, whether it was included.
Yeah, go ahead.
And yeah, we measured also nitrous oxide and could not detect any of that also from there. So that's a short answer.
Yeah, and well, it's important because wastewater sector produces. This is an important part of the greenhouse gas footprint, but it doesn't. I guess it also is generated in the open lagoons or somewhere. It's not just the burning or oxidation of fuel, but yeah, at least it's not seen in our exhaust. Then there's does the methane concentration impact the power density of the system? The system, well, given the relatively little variations in fuel quality or calorific value of the fuel, the reading that we had, the methane concentration, was used to control the flow of the fuel, because we give a current set point for the system. The system aims at providing sufficient amount of fuel and fulfilling a number of constraints and requirements within the system, but the controller, there's a request for current, and that then is converted to a request for fuel, and if the fuel becomes leaner, then we supply more. There are some interactions, but I would not say power density. Current density of the cells was kept constant or specified or defined by other factors than the fuel quality. These changes are not so major. Cell operating voltage is never constant. It's one of those things where everything can be seen. Of course, how constant it's another thing, but there are minor variations in voltage, whatever happens, if it's sunny or rainy or anything in the environment, it can be actually seen in the voltage, but because of this quite sophisticated control, which sort of maintains sort of chemical state image, sort of an image, for these minor changes of methane content don't really change voltage that much, because it's all within control, and we supply more of the fuel. It must be said that when there was an overhaul in the digester, and we had to speculate a little bit whether we got nitrogen in the process, which sort of overall diluted the gas a little bit. It's still speculative because we didn't measure nitrogen, but it was just an assumption. We obviously did see some skewing of results compared to what we were expecting to see, because there was like an unknown component in it. But it was good. We measured both CO2 and CH4 with optic sensors, and then the two independent sensors could sort of give us a good image of what kind of gas is coming in. Which type of gas processing methane reforming unit was used in the system? Did you consider anode gas recirculation? Anode gas recirculation and a pre-reformer is part of the hot process, and there's no external reforming. It's all thermally integrated, and anode gas recirculation is our means for providing water for the reforming reactions and increasing the overall fuel utilization. Are you running the system with anode exhaust gas recirculation? Yes. If yes, what is the feasible recirculation ratio? I choose not to say a number, but our system is based on an ejector, and it's our own competency, and we design and build it, so we can design the system with quite a high recirculation ratio. Now that this is a biogas application, the gas already has a significant fraction of CO2, which brings in oxygen, of course. CO2 partially, not you can't fully account it as oxygen in the system, but it partially participates in these so-called dry reforming reactions. But water comes from the anode, and we recirculate it back. In the previous seminar, there was some numbers on estimated price reduction for a new installation, but no numbers for SOFC system. How much was the price per kilowatt of SOFC at the beginning of the project, and what would you expect now? Please join us next week, because that's going to be all about economics. Price of these systems today is rather high. These are sort of pre-commercial systems, and because of all the price, both the cells and sales tax and the systems is very much dependent on production volume, and these are built one by one. Therefore, the price today is high, and that's why we are very grateful for the project and European Union for funding and making this real. This is what is needed, because in the end, the market is large and global, and we can see that particularly cell production, it resembles something like a solar cell or battery cell or electronics manufacturing. A very large number of repeated single and relatively simple units, and scaling up the production will bring down the cost tremendously. But I will discuss more of the prospects of cost next week together with Imperial College. Does the afterburner rely on catalytic combustion? No, it does not. It is an alternative that could be considered, but it is not needed because of the temperature is very high, and we can combust the residual of combustible content straight out of the stacks and at high temperature. Catalytic combustion would make a difference in one regard. When Markus can tell more, but when we did the emission measurements also across the sequence from a startup, there was like a little puff of carbon monoxide during the startup. It didn't last long, but some carbon monoxide is generated when a system is cold started. After that short period, none. It's just CO2 and water. Which is the steam to carbon for reforming? Well, it's quite high. But yeah, I choose not to disclose all the details. Have you evaluated if pressurized operation would be advantageous? Efficiency, power density may be combined with the microturbine. Yes, obviously we are engineers and we've been very curious about all the possible things, and this is one kind of something that intrigues an engineering mind. I have to say, however, that for stationary generic power generation, it would be very hard to justify, because it adds so much complexity to essentially a super simple process, and that complexity increases likelihood of failures, frequency of maintenance, and only moderately increases efficiency. I can understand if somebody wants to build a SOFC system for ships or airplanes or submarines or something like that, where space is very constrained, then it could be something worthwhile to evaluate. But still, if potential with this technology, ambient pressure technology, is 60-65% net efficiency, going to 70 is not game changing if it adds a lot of capex and increases frequency of maintenance breaks. So it's, yeah, we are interested, of course, but we've never done it. We've evaluated and analyzed it quite thoroughly at certain times, but I would reserve it for special applications where space or some other reasons, or like bottoming cycles would highly benefit from that. How many cell stacks are connected in one module? How many modules installed on site? Power rating per stack? Yeah, okay. Well, we work with different stack manufacturers. There are 2 of these Convion modules in Collegno site, and there in each we have different manufacturers' stacks. The manufacturers choose not to share the number of cells per stack publicly, but what I can say is that at this point particularly, when total volumes of solid oxide fuel cells delivered and manufactured in the world are quite low, we tap into the shared supply chain of micro CHP systems, which means that the cells are quite small and stacks are quite small as well. And therefore the number of stacks in our system is high. There are some advantages of cost advantages and maybe also robustness advantages of scaling up the stack, but there are also some challenges relating to thermomechanical stresses and quality distribution and so forth. It all boils down to where there's major demand, volume demand for components, and we'll be ready and able to accommodate them into our modules. We keep it sort of like open stack frame approach, so that whoever has the best commercially and technically most attractive stack, we can try to use it. Concerning economic feasibility, how is your experience with chromium evaporation from BOP stainless steel components? Did you use standard austenitic stainless steels parts for air heat exchangers and stack base plates, or did you have to use special steel crowfer to reduce degradation due to chromium? This is an important question, and I might have to disappoint you, not give you a thorough answer. There's plenty of discussion on chromium evaporation. One approach is that you can do many things to form a, say, alumina layer by either coating or alloying the steel with aluminum, so that it's an alumina former, but that gives you a temporary protection, and then the scaling of this alumina scaling off will then reveal the surface again, and so then that's one thing. There's another thing that by controlling humidity of the air, you can suppress the formation of chromium oxyhydroxide and the volatile chromium compounds. And then there's the last part is that what is the most important source of chromium that actually affects the stacks. Also, different stack materials are well, they have less different sensitivity to chromium poisoning, but biggest efforts are done on the stack level where contact diffusion can be suppressed, and it makes sense. In our systems, we use steel, which are chromia forming. Some optimizations have been done, but not so major changes. One thing is, of course, that stack degrades over time, and there are different mechanisms and factors affecting it, and some amount of chromium effect must be accounted for. It's part of like degradation is part of the life of the cell stacks. But we've done some optimizations, and most of the work has been done on the stack level, in the vicinity of the cells. Are there some carbon deposition issues? No, there are no carbon deposition issues because we have a careful management of oxygen to carbon and steam to carbon in the system throughout the startups. We have a proprietary process by which we don't need water, but we can arrange the conditions otherwise, and there are no carbon deposition issues. What is the afterburner temperature? It's the hottest spot in the system, but it's not very high. It's not much higher than the stack, and we try to keep it that way because the very high local temperature would cause more troubles than have benefits. Anyway, the amount of air in the process is determined by the air utilization of the stacks and thermal management of the stacks, and whatever goes into the burner is what comes out of the stacks. And but we have some means to control or suppress the temperature of the burner because it would be harmful to let it burn at very high temperature. What's the max operating pressure of the SOFC? Well, this is a so-called ambient pressure SOFC. So the pressure in the fuel cell module is low, just somewhat higher than the ambient. That is determined by the pressure drops of the heat recovery unit, the chimney, and our own sort of built-in heat exchanger for preheating the air, but it's very low. It's not pressurized in any way, and it's not controlled in any way. It is actually just resulting from the flow resistance of the components downstream. Does the biogas flow rate varying based on methane fluctuation affect the SOFC efficiency? No, we know the varying methane content, and therefore we actively control the flow rate. So flow rate varies because of our control, so that we can keep the SOFC stack in as equal conditions as possible. Of course, not totally, but very close to the same conditions always. Okay, any other questions? Very good questions, by the way. Which part of the BOP of this system was the most challenging part to be integrated to the SOFC stack? Well, first of all, the fuel cell module was not developed, what we call C50 fuel cell system was not developed in DEMOSOFC project. It was development that had been done earlier. Of course, we've learned a lot, and by doing this and operating it, and the integration part that was discussed about last week in an earlier seminar was probably the most arduous part of it. I mean, it took a lot of engineering hours. The fuel cell system itself, of course, is a result of years and years of R&D in our company and in our team. Most of know-how relates to the automation system, which controls the state within the system, given that the conditions, ambient conditions, and the fuel quality varies. We have on a process level, a process-related IPR mostly is in the fuel system, which is the fuel reforming, recirculation, and how to manage no-load transients and startups and shutdowns. This is where we probably have most of the process-related IPR. But the automation system is the heart of the system that controls the state, whatever happens and takes place in the environment. Okay, we still got one more question. What were the reforming and the stack operating temperatures in the system? Well, again, I will not disclose it on a very detailed level, but the temperature of the cell stacks is somewhat around 800 degrees C. In our process concept, everything is packaged sort of not isothermally, but in the same thermal domain, so that we don't have many heat exchangers. We have a very, very simple process, and therefore the reformer operates at close to the stack temperature. Okay, well, thank you very much for the questions. Very, I would say, educated questions, and I recognize some of your names there. Thank you very much. It was my pleasure to talk to you today. And next week we will have the final part of the series of webinars discussing about economics of this application and SOFC in it, and also to some degree in general. I wish to welcome all of you to the
Thank you, Thomas.
Webinar next week. Well, thank you.
Thank you very much, Thomas.
Thank you, Thomas, and thanks to everybody for joining this seminar.
Thank you also from my part. Thanks.
Thank you, Markus.